I'm going to make this lesson hopefully nice and short and sweet if you're already good at rectangular approximation, left-hand rectangles or left Riemann sums, right rectangles, right Riemann sums, and midpoint rectangles. We're not going to go anything crazy different. So why would we need something else if we were going to approximate? I just made some function f. If we were going to approximate the area under f using left rectangles, well, you can see that rectangles don't do a phenomenal job approximating the area under this curve. We have lots of areas that are too small, lots of areas that are too large. That doesn't change, I guess, whether we have what appears to be an over-approximation or an under-approximation changes, but we still have, well, too much, too little, too little, too little, too much over here. Well, probably not the right area, or at least very obviously not the right area, using right rectangles. But what about midpoint rectangles? Hey, they're kind of better, you know, this little triangle and this triangle, a little too much and a little too not enough. They seem to kind of cancel each other out. So that seems pretty good. And it is, but there's an alternative to midpoint rectangles, and it's actually a pretty straightforward formula. So if we're using trapezoids, you can see, well, a lot of the time, hey, that trapezoid does a really good job of getting the area under a curve. And, you know, even somewhere up here, that's not horrible. You know, I bet that this is a pretty darn close approximation. So that's, you know, at least what we're doing. So you should be able to use trapezoids to approximate the area under a curve. And because we're getting you ready to pass the AP test, you have to decide when to do formula work, because like everything else, there is a formula, and when to use separate trapezoids to estimate area. First, how do you find the area of a trapezoid? Well, the parallel sides are called bases, and the area of a trapezoid is the average of the bases. So base 1 plus base 2 divided by 2. I just like it this way. Multiplied by the perpendicular dimension, I'll just call height, even though that seems weird. And what that really does is we get a rectangle with the exact same area, but this height of the rectangle is the average of those two bases. And if you want a graphical argument for that, I think I can provide that. So right here at the midpoint, we're going to draw this perpendicular bit, and I guess we can extend that over here. And if I've drawn that correctly, you know, through the midpoint, these two lengths are the same. These two lengths are the same, and vertical angles are congruent. The right angles are congruent. These are congruent triangles. So it's like we, you know, cut this piece off and filled it in over there. So we're going to need that area of the trapezoid formula. So we're going to approximate the area under f on 0 to 10, and we have no idea what f looks like. We just have a bunch of ordered pairs. You know, what does f look like? You know, maybe f looks like this, but no guarantee. You know, maybe f looks like this. We have no idea, and so no matter what, you're going to have to use finite approximation. You know, you could probably predict, if we were given some sort of context, what's happening in there. And so, you know, all we're going to do is make a trapezoid here, and another trapezoid there, which happens to, well, the two y values are the same, so we're going to act like a trapezoid, but no, that's a rectangle. And trapezoids here. And the reason I'm starting with this problem is hopefully you'll notice, you know, this first width, or change in x. Ooh, I'm sorry, I'm working at home and I don't have, you know, my normal setup here. So the change in x here, let's call that change in x1 is 1, and the change in x here is 2. And you know, one of the objectives was decide when to do formula work and when to do separate trapezoids. Students will think, oh, you know, formulas always work. Well, yeah, I mean, kind of. Like, the formula for area of a trapezoid always works. But the formula we're going to get to at the end of this I guess only works if you're using the exact same widths. Trapezoids are, you're multiplying by the same width every time. Let's see. So what does this look like? Okay, I wanted to go back here. And so how do you find the area of a trapezoid? Well, the first trapezoid is going to have a width of 1 minus 0 and a height of, let's just say a height of 4 plus 3 over 2. Or a height of f of 0 plus f of 1 divided by 2. And then our second trapezoid is going to have a width of 3 minus 1. And it's going to have a height of 3 plus 3 divided by 2. So we're just using the trapezoid thing without thinking, even though we already know, hey, that's a rectangle since the two y values are the same. A new color. So that's going to be 6 in x value minus 3 in x value right here. And then that's going to be the average of the two y values. Let's see, 1 plus 3 over 2. And let's see, from 6.6 to 6, we get a width of 0.6 times an average height of 5 plus 1 over 2. Plus, let's see, 8 minus 6.6 times an average height of 8 plus 5 over 2. And I think I can squeeze that last one. Plus 10 minus 8, that's the x's. Pretty obvious, 10 minus 8 times 10 plus 8 over 2. And that's it. Kind of annoying and straightforward at the same time. I don't know. It's just, hey, a whole bunch of trapezoids, and you can do that on this graph if you wanted to. Let's see. So what would this left trapezoid be? Well, that would be, that's a width of 1, which we did previously, 1 minus 0, and a height of, or an average height of, what is that? That's 4 plus 3 divided by 2, or 3.5. And that does seem about right. So this area is 1 times 3.5, or 3.5. But it's a little bit easier to write this stuff out, I guess. So let's do the formula thing, because really that's it. It's, hey, adding a bunch of trapezoids together. And so here we go. The table above, or to the left, let's just pretend like that says to the left. The table to the left shows the velocity of a bobsled at 1-second intervals for the first 8 seconds of its run. Use the trapezoidal rule to approximate the distance that the bobsled traveled during those first 8 seconds. So I'm going to try to show you, what I mean by pattern. And so I'm going to do, well, let's see. Let's think about this, because we're at least finding area. And, we're going to have to do some sort of conversion. So miles per hour, and multiply that by seconds. And, well, we need to multiply, we need seconds. And those aren't exactly going to divide out. And so I want to get rid of hours. So let's see, 1 hour over 3,600 seconds. And oh yeah, sweet. We're going to get the number of miles, and so yeah, that looks like distance traveled. I suppose we could change the times too, but let's just worry about the numbers. So I'm going to do this a little bit differently. The first time, or at least maybe all of the times, from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 5 to 6, 6 to 7, 7 to 8, that's all, a change in time of 1. Or we could have done, how many intervals are there? 1, 2, 3, 4, 5, 6, 7, 8. So we could do 8 minus 0 divided into 8 equal sized pieces, which of course gives us, 1. Okay. And then, let's see, what would the first height be? Well, that would be, and I'm going to write this a little bit differently. So let's say it's the velocity at 0 plus the velocity at 1 over 2. And then, oh, I need big brackets, because I think we're all okay with that time out front. And then my next one's going to be the velocity at 1 plus the velocity at 2 over 2. That's that second average height. And then where are we going? Let's write them all out. Plus the velocity at 2 plus the velocity at 3 averaged. And, you know, maybe I'll write one more. This is ridiculous for you to watch me write. And then maybe we should write the last two. So the last two are going to be, let's see, the velocity at 6 plus the velocity at 7 over 2. And the final one, maybe end on orange pen. The velocity at 7 plus the velocity at 8 divided by 2. We didn't skip too many pieces. But, you know, what do you notice? Well, everything's divided by 2. Every single term on that inside is divided by 2. So, you know, we could have 8 minus 0 divided into 8 equal sized rectangles, and we could, you know, put that half out front. So we'd have, you know, all of these 2's gone. And if all of those 2's are gone, well, those parentheses don't matter at all, do they? And if those parentheses don't matter, maybe I'll just write that one half here so everything matches. If those parentheses don't matter, then what would we have? Let's see. Goodbye. Probably that plus sign matters. I'll go back and put that in. What color were they? Well, you have, you know, v of 0, or evaluated kind of on that left-hand endpoint, plus 2v of 1s, plus 2v of 2s, plus 2v of 3s, you know, all the way to, well, we're going to have 2v of 6s, even though I didn't write that, 2v of 7s, and just 1 v of 8. And so that's our formula. And you know what? Why is that the case? Well, v of 0 and v of 1 are in that first trapezoid. And in that second trapezoid, you have v of 1 again, but on the right-hand side is v of 2. And let's see. For the third trapezoid, v of 2 is on the left, and then, you know, v of 3 is on the right. Every single interior input value is used twice, and just those endpoints are used once. So what's it going to look like in a book? Well, b minus a over n up front isn't too crazy. You saw that the 1/2 right here was factored out, and then just, hey, f of, or the function evaluated at the left-hand endpoint, evaluate the function at 1 width away from the left-hand endpoint. There are going to be 2 of those. And then, you know, 2 widths away, 3 widths away, 4 widths away from the left-hand endpoint. And by the time you get to, hey, this last one, hopefully you can see, well, we should be evaluating at b, and so let's see, let's make sure that happens. F of a plus, the n's divide out, b minus a is f of b. So we end up evaluating at that last endpoint. I don't know, maybe the most important thing is last, and that's, hey, you can only use this for uniform width trapezoids. And what I see every year is I get it, and it's sort of easy, but students will be given data like this. They're like, hey, you know, this is the problem we did earlier. Hey, from 0 to 1, you know, that's a width of 1, and they don't notice that all these other widths are different. You know, one of them is 2, and one of them is 3, and one of them is 0.6, and they just write, well, okay, so it's going to be 10 minus 0, you know, divided into 1, 2, 3, 4, 5, 6. How many pieces is it? 1, 2, 3, 4, 5, 6 equal sized pieces. And then, you know, weirdly, you end up with a width that's, you know, kind of nowhere on here. So that's kind of the big warning.